As CAD and CAM software progress in capability and complexity, machinists across the industry are seeing an increase in production-ready parts, with the parts themselves increasing in complexity. Combining CAD and CAM into a single integrated environment is even more powerful, allowing the time between iterations to decrease significantly. In an integrated CAD-CAM environment, when there are design improvements, the machinist can simply regenerate the existing toolpaths using the new geometry, and then make any additions or tweaks as needed. The conversation between designer, engineer, and machinist also becomes much more coherent, since the design and manufacturing software are taking place in the same platform, giving a common and familiar backdrop. Very few designs have ever made it from conceptual design to production part without changes. Feedback from the machinist on what can and can't be manufactured given the current capability of their tools is imperative to the success of producing the part. Integrating CAD and CAM offers the ability to easily switch between CAD modeling and CAM programming, cutting out the pain of exporting, switching software, importing, and then finally starting the conversation. So let's dive into some common manufacturing processes used in industry. Subtractive manufacturing, also referred to as machining, is essentially the controlled removal of material. Subtractive manufacturing can take many forms, but it is typically a process where a cutting tool, like an end mill, removes material from a solid block called the stock. The material is often removed over several passes, since tools can only remove so much material at a time. The basic parameters used when determining the path the tool will take are step over and step down. The step over is the lateral or radial amount of material the tool is removing. Step down is the vertical or axial amount of material the tool is removing. Manual mills and lathes, where the cut is controlled by hand, were once common, but are becoming harder to find as time goes on. Now subtractive manufacturing is often achieved using a CNC machine, where the cut is executed by a small computer called a controller. This is where CAM software enters the picture, as the code the controller executes is generated using the CAM software. In a small prototyping environment, a shop might have a smaller CNC machine and possibly a manual machine. In a medium-sized job shop, there will be several CNC machines with varied capabilities. Jobs in this environment might go through several machines before they're completed. In a full production environment, a factory floor can be filled with machines of the same type, all running the same job. Typically, the stock is automatically fed into the machine, and the part can be manufactured with minimal human interaction. In addition to capable CNC machines, the quality of the toolpaths the CAM kernel generates is important to manufacturing success. Traditionally, toolpaths were simply offset passes calculated using the constant step down and step over parameters. These toolpaths are reliable, but increased forces on the tool in internal corners often lead to breakage without precautions like reduced feed rates. Constant engagement roughing toolpaths, like Autodesk's adaptive clearing, use algorithms to keep a constant engagement on the tool, effectively keeping a constant load on the tool and allowing faster and deeper cuts than the traditional toolpaths. This is important for production shops, where saving seconds per part, multiplied by the hundreds or thousands of parts produced, can make a significant impact on productivity and ability to meet production deadlines. Keeping the tool load constant and spreading the wear across the entire flute length also improves process reliability and reduces tool breakage. Every tool break means a tool replacement, which can take several minutes, a significant process in a production environment where seconds count. Constant engagement strategies enable machinists at all levels to push their machines faster, increase productivity, and improve process reliability, from prototyping to high production environments. Another common manufacturing process is additive manufacturing, which is controlled material addition and is commonly referred to as 3D printing. Like subtractive manufacturing, additive manufacturing can also take many forms, but typically involves adding material layer by layer until the final part is achieved. Since material is being added rather than removed from a solid block, there are features and shapes additive manufacturing can achieve that are nearly impossible in subtractive manufacturing. Internal latticing, sharp internal corners, and tall vertical walls are all much more accessible when produced with additive manufacturing. For hobbyists and makers, additive manufacturing is very accessible with low-cost machines that deposit relatively large layers and use plastics like ABS and PLA. These are usually fused deposition modeling, or FDM, where the plastic is pushed out of a heated extruder, and lower-end FDM machines often do not support material. Additive manufacturing services for those who do not want to invest in an entire machine are also available. In a medium shop, there are professional-level additive machines that have large build volumes, use several materials at once, and print a separate support material, which allows for more complex geometry. These can also be FDM and are sometimes stereolithography, or SLA, where a liquid resin is cured using a projection of the layer geometry. At the highest and most innovative level of additive manufacturing, selective laser sintering, or SLS, can be used to make parts in plastics and metals by using a laser to solidify a powder into solid parts. The ability to create features that are exclusive to additive manufacturing in strong materials like stainless steel and aluminum broadens the horizons of what manufacturing can achieve and continues to accelerate the development of manufacturing design, software, and hardware. Perhaps the most exciting development in production manufacturing is the combination of additive and subtractive manufacturing, or hybrid manufacturing. Additive manufacturing has opened up the possibilities of what can be produced by removing many of the design challenges associated with subtractive manufacturing. In particular, lightweighting strategies like topology optimization and internal latticing are significantly more accessible using additive strategies. From small startup operations to full production products, the ability to reduce weight while maintaining strength allows increased innovation and high product performance. There are, of course, downsides to additive when compared to subtractive. The materials that can be used are limited, it is much slower, and it is much less accurate. But that's where hybrid manufacturing comes into play. A currently used method leverages a full additive part that is inspected and then finished using subtractive manufacturing to bring critical surfaces to the required tolerance or surface finish. The door is also open to develop true hybrid machines that deposit material and then machine the deposited material to the required tolerances. There is immense potential in hybrid manufacturing to improve the quality of produced parts while simultaneously reducing material waste. As progress is made in the materials and accuracy additive manufacturing is capable of, and in the ability of generative design software to produce valid and improved designs, hybrid manufacturing will truly play a significant role in the future of manufacturing.